This is Mrs. Palmer Quay with the first video for Module 4. In this video I want to talk briefly about mixtures and how we can separate the components of mixtures. To start with a little bit of review, remember that matter can exist as a pure substance or a mixture. Pure substances consist of our elements, all the same kind of atom, and compounds, two or more different kinds of atoms that are held together by chemical bonds. In pure substances, you always have the same proportion of the different ingredients, the different elements for any one compound, and these ingredients are existing in the same phase in that compound. A pure substance the components of a pure substance can only be separated by a chemical process. A chemical reaction has to occur, and what particular reaction that is depends on the chemical properties of whatever element you're talking about. But you're going to need to change things chemically in order to separate out the elements in a compound. A mixture, in contrast, can have varying proportions and still be called the same mixture. And I think this will become clearer as I get to the next slide. In a mixture, the ingredients may all be in the same phase, or they may exist in different phases and be part of that mixture. And we can separate out the components of a mixture by physical means based on their physical properties. Getting a little bit more specific about mixtures, they exist as two types, homogeneous or heterogeneous. And this should be red. Sorry, I didn't manage to get that color change. But homogeneous mixtures have a composition that is uniform throughout the mixture. It seems to be the same all the way through. And it often can be confused then with a pure substance because it looks like it's the same all the way through. So in a homogeneous mixture, all of your ingredients exist in the same phase. In the heterogeneous mixture, the composition is not uniform throughout the mixture. You can see different things. And because of that, the ingredients may be existing in different phases. So this cup of coffee is a homogeneous mixture. It has all of the brewing has happened and we have the coffee particles suspended in solution. Things that are in solution are homogeneous mixtures. Vinegar is acetic acid in solution. That's a homogeneous mixture. Seawater, salt water, is again a solid that has dissolved into the water, so it is a homogeneous mixture. The heterogeneous mixtures here on the bottom include things like milk, which look like it might be a homogeneous mixture or a pure substance. But if you wait long enough, and especially if you purchase raw milk, you know that cream will rise to the top. It will separate itself out. And so if you look in more detail, you can tell that there are different particles. They are existing, some solids suspended in liquid, actually in milk. I know you can picture the solids suspended in the liquid of Italian salad dressing, the little bits of seasonings that are in there. And if you make homemade salad dressing, you know that the oil and the water only stay mixed together for a very short period of time. They separate out very quickly, and so it's obvious that these contain two different substances in this mixture. Also, you know that any particular recipe for salad dressing might have a tiny different amount of olive oil versus water versus vinegar, but we still call it salad dressing. Carbonated beverages are also a heterogeneous mixture because gas is dissolved in a liquid. So we've got two different phases present, and as that soda sits over time and goes flat, the proportions inside that liquid also change. Your toothpaste is actually a liquid dissolved in a solid, and that's what gives it that gel component. So it is also a heterogeneous mixture. So the top half of this slide are all of the homogeneous mixtures, and then the bottom half are examples of heterogeneous mixtures. There are several ways that you can separate out the components of a mixture. I just want to go through three of the most common. Filtration is a method that separates solids from liquids. And so just to give a very simple example, if you have a mixture of water and sand, and you pour that mixture into a funnel that's been lined with filter paper, the water, of course, will drip right through, leaving the sand behind. And so filtration, the use of filter paper, separates solids from liquids. In the human body, your kidneys filter out plasma from the red blood cells and some of the larger proteins in the bloodstream, and then that plasma, the filtrate that goes through the kidneys, is further adjusted so that just the right substances are excreted and the ones that need to be saved are carried back into the body. Distillation is another process for separating mixtures. It separates liquids based on their boiling points because different liquids will have different boiling points. We're not going to do any distillation in class because it requires some equipment we don't have. I have an illustration of a distillation setup here. When we use distilled water in our labs, it has been separated from the dissolved minerals that are found in the natural water source, so it's water that has been separated out by distillation. Hard liquors, brandy and such, are formed by distillation of the fermented base that started the whole process. It has a higher alcohol content because alcohol has a lower boiling point than water, so it will go through the process sooner. And most of our petroleum products are actually distilled from crude oil. So gasoline boils off at a certain temperature, kerosene at another, and that's how we separate them. So in the distillation process, you've got your liquid mixture here that needs to be separated. As it is heated, whatever component has the lowest boiling point will turn into a gas, which flows down this tube. In this tube, we have cool water, so it causes it to condense. It changes back into the liquid state, and then it is collected over here in the flask. And then finally, chromatography separates a mixture based on the attraction between the components of the mixture and the various solvents used in the apparatus. Some types of chromatography are analytical. They just analyze what is in there. Other ones are preparative. They prepare pure extracts of whatever mixture you started with. So paper chromatography separates components of a dried liquid sample by using a solvent and a paper strip. And this is an example down here, an illustration of somebody that is separating out the components of this black ink to show that in that black you've got some blue and some green and some purple, some other colored dyes all together that turn it black. Paper chromatography, just to give you a real-life example, is used to determine the pollutant level in water. Liquid chromatography separates components of a liquid sample by dissolving that liquid in another liquid, in a liquid solvent, in some sort of column that's been packed with some material that slows down the process of the liquid dripping through. And so we've got our sample up here at the top of this column. It's a mixture of proteins. The solvent is continuously applied, and it carries things down this tube. And the proteins, based on their attraction to that solvent, will separate out and can be collected as pure extracts down here at the end. This technique is used to separate proteins from a mixture produced through the recombinant DNA techniques. Things like human insulin are produced by using bacteria that have had the DNA altered in order to have them make insulin, but they also make other proteins, and so you have to use a process to pull out just the insulin from the whole big mess of proteins that are there. And finally, gas chromatography separates a mixture of gases and again uses a carrier gas, this is like the solvent, and a column of liquid or solid beads, something that will slow down the process. This technique is used to analyze blood alcohol levels in hospitals, and we see that is a very elaborate setup, certainly not something we can do in class. But the sample is here, and it's mixed with the carrier gas and then sent through a detector, and results then printed out. And this has been a very helpful technique for many of the analyses, both in crime scenes as well as in hospital uses. It never happens as quickly and as neatly as it happens on those crime shows, though. Real life science is a whole lot messier. So that covers what I wanted to say in this short video about mixtures and how we can separate out the components of mixtures.